Okay, anyone else have a heart attack today? Just me?
Oh, what happened?
I was gonna go, so I'm leaving tomorrow. I'm gonna
the-
take a flight.
Uh-huh.
I thought my flight was 11:30 p.m. United has a flight at 11:30 a.m., which is what I booked. Now, who in their goddamn right mind books a flight or puts, I mean, just make one 11:25 and the other 11:30, and that way you can't mess them up. I'm flying with a friend. She's like, no, my flight is 11:30 p.m. I was like, excuse me? Anyway, so that's my life. Um, Unusually I have. So because I travel a lot for work, usually I'll pack the morning of or the night before. Since I'm going to Iceland for 7 days and the temperature there is on average 0. It's a little cold. I I decided that I should make sure not to miss anything. So we'll see. I might die. But that's the point of living. If you really think about it. It's a learning experience. That's what they all say. So let's give folks a few minutes to arrive. Otherwise we'll just jump into how to do faster methods. Someone want to take faster methods? Andrew just went, so doesn't have to go again. Gonzalo, you ready to present on faster methods?
Guess I'll take it by phone.
I mean, it's a question. You want to do it?
What section is it?
9.2?
Okay. Yeah, I'll do it.
Okay. And you have notes on it already? If you're seeing it for the first time, that's really not how we present, right? We don't just read out of the book. We want to summarize what we think are the important parts. Okay. So I would always recommend, of course, reading before we start. I've read this a number of times, so I'm going to demonstrate for you how I would go through this process. What we're talking about here is we were talking about these boundary value problems, okay? And this process of solving the Poisson equation, which was this one right here. All right. Here's the Laplacian, which is written like that, where we're looking for the charge inside of an area, and we're going to solve it appropriately. So we would do the same thing here. The only difference is we're going to see if we can do it faster. So the method that you used before, where you just write over the entire array and then you swap them, that's a method called the Jacobi method, okay? It's slow. So we want to go faster, okay? So the problem 9.1 solves 10,000 simultaneous equations for 10,000 unknowns, one for every point on the 100 by 100 grid, okay? I forget how long it took you, but maybe like a few minutes in between every run, right? You'd like wait. Yeah, like literally taking a long time. And when we think about computers, usually the runtime is the major cost. So you think to yourself, what do you mean cost, Grismani? Well, right now your computer's turned on and it costs a certain amount of electricity. You can imagine that with much larger computers like supercomputers, those will cost a great deal more to run, right? So if you're running something on a supercomputer for a month, that costs money, right? Okay. So let's find faster solutions that still give you the same accuracy. The first one is called overrelaxation. So it says on each iteration of the Jacobi method, the one that we used before, the values of phi were updated one by one by one by one by one. Overrelaxation says, I'm going to be a little aggressive here. I know that the slope is like this. I'm just going to crank it up a little bit and try to jump faster towards that solution. Does that make sense? So let's look at the Laplace equation here. It's this value is equal to the original value plus whatever change we were going to add to it. Do you remember what that little change was? Yeah, it was like the one above, one below, one to the right, one to the middle, right? Divide by that. add whatever, right? That's the little bit, okay? So all we have to do now is say, well, let's just do that same plus a little bit, right? Now, this is not 10. It's like 0.3, 0.4, 0.5. And you can play with this omega like it's a dial to see whether you can get it to converge quickly, right? Get the solution to come out very quickly. Or, if you make it too large, you're going to break it because now it's not going to be able to converge at the right solution, right? And what you'll see here is when we substitute this in, we have some of the same things we had before. Here's phi xy. Let me just zoom in a little bit for folks online. Oh shit. Okay, so we have phi xy. We said it's the one to the right, one to the left, one above, and one below. And we're going to divide that by 1/4. But now it's not quite 1/4. It's 1/4 and a little bit, right? And similarly, we're going to subtract where we are by a little bit. So it's omega times that value. Does that make sense? Okay, good. That's overrelaxation. You can add to this another thing, okay, a second trick. And this is what we call the Gauss-Seidel method. And here you can kind of see in this image, this would be like starting at the top of the array, and then you move through the array, and then you go down to the next row, move through the array, go down to the next row, right? And then this is stuff you have to do, and this is where you are. What this method says is rather than having two arrays where you update one and then switch them, what if you just use a combination of the old and new information? So if I'm right here at this array, even though I've updated the one behind me and the one above me, I'm not going to use the old ones. I'm going to use the new updated ones. And I'm going to combine the stuff that I've done with the stuff that I have to do. Is that reasonable? So that saves us one array. Thinking about it in terms of memory costs, if you have to build tons of arrays, that could be expensive computationally, right? Okay. And then there's the Gauss-Seidel method. It's Gauss-Seidel method. Adding overrelaxation is the same way. And you see the only difference here? Before, this was phi prime. And now it's just phi on both sides, right? So that doesn't look different at all. It just looks like phi and phi. Your new phi is simply all the values around you. And you still walk through the entire array and update every single one, right? Okay. Reasonable? That's quick, right? Okay, let's do it. I mean, yeah, we could have got some free points there, but